Hello, my dear students. Congratulations for reaching this far. We are now on the last lesson in basic calculus, the Riemann sum and the definite integral. Today's lesson, we have the following goals. Approximate the area of a region under a curve using the Riemann sums, left, right, and the midpoints. Define the definite integral as the limit of the Riemann sums, and solve real-life problems involving areas of plane regions. All aboard! Most of the time, figures with irregular shapes are more exciting and appealing. Hence, designers often use these shapes to make their work distinct and catchy. Usually, lots are not in regular shapes, especially if it is bounded by a body of water. Architects and engineers need to know the area so that they would be able to design a structure which can perfectly fit in that particular lot. As a student in basic calculus, it is important to know how to find the area of irregular shapes in order that you become the best that you can be in the track which you have chosen. But how do we get the area of a lot having a regular shape? Geodetic engineers conduct land survey, and then they perform computations in order to know the area of that particular lot. In basic calculus, we have several ways to find the area of a lot having a regular shape. The first method is using the Riemann sum formula, which is defined as the definite integral of f of x on the closed interval from a to b. This is equal to the limit of the summation of f of x sub I times b minus a all over n, where I starts from 1 up to n and approaches to positive infinity. Or we can have the limit of the summation of f of x sub I times delta x, where I starts from 1 up to n and n approaches to positive infinity. The Riemann sum formula is like adding all the rectangles that can fit in to that particular area. We can have the first type, which is using the left vertex of the rectangles, and we call this as the left Riemann sum formula. We can also use the right vertex of the rectangles that can fit in that particular area, and that we call as the right Riemann sum formula. We can also use the midpoints of the segment or of the side containing the left and right vertices of the rectangles, and we call that as the midpoint Riemann sum formula. All of these are used according to the area bounded by the curve. So let's have the first example. Approximate the area bounded by the following functions. Y equals 1/2 x squared, x equals 1, x equals 2, and y equals 0. Now, to facilitate our understanding, let's visualize using graphs. Using GeoGebra, we can have this visualization. We have the green curve representing the function y equals 1/2 x squared. The vertical line is x equals 1, and the blue vertical line is x equals 2. Whereas y equals 0 are represented by the red horizontal line. So in this case, we are asked to find the area of this region. Now first we have to determine that closed interval at which the function is considered. So with the given example, we have A, and then we have B. We are only considering this function at a closed interval from A to B. And then we draw rectangles having the same width. So with this, we can have delta x to represent the width of the rectangles. Now let's say we decided to use 5 rectangles, and then we can get the value of delta x using this formula. Now let's start by identifying the values of A and B. With this particular example, we are considering the closed interval from A equals 1 and then B, which is equal to 2. Now, since we have decided to use 5 rectangles, we would be able to get the value of delta x. Using the formula, delta x equal to b minus a over n, we would have 2 minus 1 divided by 5 will give us 1/5 or 2/10. Now from here, we can form subintervals which are from 1 to 1.2, from 1.2 to 1.4, and then from 1.4 to 1.6, 1.6 to 1.8, and lastly from 1.8 to 2. Now let's say we decided to use the left Riemann sum formula. We can draw the rectangles and use the left vertex of this rectangle. Now to get the length and the width of this rectangle, we can have f of x sub 1 for the length and the width, which is delta x. Now we can evaluate this function in order to get the length of the first rectangle. So evaluating, we will have 1/2 of 1 squared, that is equal to 0.5. Now let's have the next rectangle. To get the length of the second rectangle, we need to use the left vertex of this rectangle. So evaluating the function at the second value of x, which is 1.2, we would be able to get 0.72. Doing the same thing, the third rectangle, we will evaluate the given function at x equals 1.4. So we will have 0.98. And then we have the fourth rectangle. To get the length, we will have 1/2 times the third value, which is 1.6. So we will have 1.6 raised to the second power. We can have 1.28. And for the last rectangle, we can get the length of the rectangle by evaluating the function at x equals to 1.8. Simplifying this, we will have 1.62. Now to get the area of the region bounded by these functions, we can get the sum of the areas of these rectangles. To get the total area, we can use delta x times the length of the first rectangle plus the length of the second rectangle the length of the third rectangle plus the length of the fourth rectangle, and then the length of the fifth rectangle. So replacing the variables, delta x is 2/10. Now take note that L sub 1 is 0.5, L sub 2 is 0.72, and then L sub 3 is 0.98. The length of the fourth rectangle is 1.28, and the length of the fifth rectangle is 1.62. Now getting the sum of these lengths, we would be able to get 5.1. Now multiply by 2/10, we will have, hence the area of the region is approximately equal to 1 200 square units. Now let's try to use the right Riemann sum formula in approximating the area bounded by the given functions. We start by identifying the closed interval at which we consider the curve y equals 1/2 x squared. As given in the problem, we have a is equal to 1 and b equals 2. Now, since we decided to use 5 rectangles, then we can find the value of delta x, or the width of each rectangle. So, using the formula, delta x equals b minus a all over n. Now, since we have b equals 2 and a equals 1 and n is equal to 5, delta x is equal to 1/5 or 0.2 or 2/10. Now with this, we can form the subintervals 1.2, 1.2 to 1.4, 1.4 to 1.6, 1.6 to 1.8, and 1.8 to 2. We start drawing our rectangles. So our first rectangle would have a width of delta x and a length of x sub 1. Now, since we are considering the right vertex of the rectangle, we shall have x sub 1 equal to 1.2. Now, evaluating y equals to 1/2 of 1.2 squared, we shall have 72 hundredths. Now for the second rectangle, we will still have delta x as the width, and then for the length, we will have the second value of x, which is 1.4. So evaluating the function 1/2 times 1.4 raised to the second power, we shall have 0.98. We continue the same procedure. So we would be able to get the length of the third rectangle by using x equals to 1.6. With this, we would be able to get 1.28. Now to get the length of the fourth rectangle, we will evaluate the function at x equals 1.8. So we will have 1/2 times 1.8 raised to the second power. That will give us 1.62. Now, looking for the length of the fifth rectangle, we will evaluate the function at x equals 2. Okay, we use the right vertex having an x coordinate of 2. Now evaluating, we will have 1/2 of 2 raised to the second power. We will have 2. We can use the formula delta x times the sum of the length of the rectangles, replacing delta x by 0.2 and all the other variables by their values. Adding this, we shall have 6.6. Multiplying by 2/10, we shall have 1.32. Hence, the approximated area of the region is 1.32 square units. That is using the right Riemann sum. This time, let us use the midpoint Riemann sum formula in approximating the area bounded by the given functions. Just like what we did in the previous solutions, we have to determine the closed interval at which we have to consider the given curve. So we start by identifying the value of a and b. Here we have a equals 1 and b equals 2. And since we decided to use 5 rectangles, we would be able to determine the value of delta x, which is the width of each rectangle. So using the formula, we would be able to get 2 minus 1 over 5. Simplifying, we will have 1/5 or 2/10. From here, we would be able to come up with 5 subintervals. We have the subintervals from 1 to 1.2, 1.2 to 1.4, 1.4 to 1.6, 1.6 to 1.8, and 1.8 to 2. Now, using the midpoint of these subintervals, we would be able to get the length of each rectangle by evaluating the function at x equals to these midpoints. So let's find the length of the first rectangle. So from 1 to 1.2, the midpoint would be 1.1. Now, just like what we have done previously, we can get the length and the width of these rectangles, okay, by evaluating the curve or the function 1/2 of x squared. So we shall have 1/2 of 1.1 raised to the second power. So with this, we will have 0.605. Now for the second rectangle, the midpoint of the second subinterval is 1.3. And using 1.3 for x, we would be able to evaluate the given function and arrived at 0.845. Now for the third rectangle, to get the length, we get the midpoint of this. So that is 1.5. Then we would be able to get the length and the width of this rectangle. Evaluating the function at x equals 1.5, 1.125. Now for the fourth rectangle, we shall use the midpoints of the subinterval from 1.6 to 1.8, so we will have 1.7. Then we get the length and the width, so we evaluate the curve at x equals 1.7. Simplifying this, we will have 1.445. And for the last rectangle, we shall do the same. The midpoint of the subinterval is 1.9, and to get the length and the width of this rectangle, we use this. So we shall have y equals 1/2 of 1.9 squared. So simplifying this, we shall have 1.805. To get the total area, we have to get the sum of the area of the rectangles. So we can just multiply the width times the sum of the lengths of the rectangles. So delta x is equal to 2/10. Then the length of the first rectangle is 0.605. The length of the second rectangle is 0.845. For the third rectangle, the length is 1.125. For the fourth rectangle, we have 1.445. And the last rectangle has a length of 1.805. Now, adding the lengths of the rectangles, we will arrive at 5.825. Multiply it by the width, that is 0.2, we will get 1.165. Hence, the approximated area of the region using the midpoint Riemann Sum Formula is 1.165 square units. I hope you were able to get that and compare the values or compare the process of each type of Riemann sum. Now let's have another example. Approximate the area beneath the curve f of x equals x squared plus 5x plus 8 and above the axis from x equals -4 to x equals -1 with n equals 3 using the three types of Riemann sum formula. Now first we graph in order to visualize the region that we are referring to. So here's the graph of the function f of x equals x squared plus 5x plus 8, whereas we have the blue vertical line for x equals -4 and then x equals -1 for this, the vertical line with pink color. So we are asked to approximate the area of this region. Now, all we have to do is to draw rectangles, 3 rectangles, since we are given n equals 3. So let's start with the left Riemann sum formula. Now let's use the left Riemann sum formula in approximating the given area. So we have to determine the closed interval at which the curve is to be considered. So we have a equals -4 and b equals -1 as indicated by these functions. Now, since we are asked to use n equals 3, we have to use 3 rectangles in approximating the area of this region. So using the formula for delta x, we would be able to find the width of the rectangle. So if we will have b -1 and then a is -4, we will divide this. Now using the formula for delta x, we would be able to get the width of the rectangles. Replacing the variables with its given values, we will have -1 minus -4 over 3. Simplifying this, we will have -1 plus 4, and then we will have 3 over 3, which is equal to 1. So therefore, the width of the rectangle is 1 unit. So from here, we would be able to come up with 3 subintervals from -4 to -3, -3 to -2, and from -2 to -1. Now let's draw the rectangles. So we will have the first rectangle. Now since we are using the left Riemann sum, we are going to consider the vertex, the left vertex of the rectangle. So we have here this vertex. Okay, and the first rectangle is on the first subinterval from -4 to -3. Now to get the length of this rectangle, we will evaluate this function f of x equals x squared plus 5x plus 8 at x equals -4. Now using our calculator, we will have f of -4 equal to 4. So therefore, the length of the rectangle is 4. And the width, its width is 1. Now let's have the second rectangle. The second rectangle lies on the second subinterval from -3 to -2. Now we are considering the left vertex. Now we evaluate again the function f of x equals x squared plus 5x plus 8 at x equals -3. Evaluating that, we will have length equal to 2. The width of this rectangle is also 1. Now let's have the third rectangle. The third rectangle lies on the subinterval from -2 to -1. Since we are using the left Riemann sum, we are going to consider the left vertex. So evaluating the given function f of x equals x squared plus 5x plus 8 at x equals -2, we will have length equals 2. The width of the rectangle is also equal to 1. Now, to get the area of this region, we have to get the total of the area of these rectangles. So since we have width is 1, we get the sum of 4, 2, and another 2. So the area is approximately equal to 8. So using the left Riemann sum, the area of the said region is approximately equal to 8 square units. This time, let's use the right Riemann sum formula in approximating the said region. So we start with the closed interval. We still have from -4 to -1. Now let's have the width. Since we have n equals 3, then delta x is still equal to 1. So with this, we shall have 3 subintervals from -4 to -3, from -3 to -2, and from -2 to -1. In these subintervals, here lies the rectangles, the 3 rectangles. So we draw. Now we consider the right vertex. So in the first subinterval, -4 to -3, we have this rectangle, and we consider this right vertex. So in order to get the length of this rectangle, we evaluate x squared plus 5x plus 8 at x equals to -3. Evaluating the given function, we shall have L for length equals 2. Okay, its width, remember, is equal to 1. Now for the second rectangle, it lies on the second subintervals, and then we consider the right vertex. We evaluate the function at x equals -2. Evaluating the function, we would be able to get the length that is equal to 2. The width of this rectangle is equal to 1. Now for the third rectangle, we shall have the third subintervals from -2 to subinterval from -2 to -1. Now to get the length, we evaluate the given function f of x equals x squared plus 5x plus 8 at x equals -1. Evaluating that, we would be able to get 4. So the length of this rectangle is 4 and the width is 1. Now to get the total area, so since we have to get the total area, we have delta x times L sub 1 plus L sub 2 plus L sub 3. Delta x is 1. The length of the first rectangle is 2. The length of the second rectangle is also 2. And the length of the third is 4. So we shall have 8 for the total area. So using the right Riemann sum formula, we also have 8 square units. Now this time, let us use the midpoint Riemann sum formula. So again, n is equal to 3. Therefore, we'll still have 3 subintervals and 3 rectangles to be used. But this time, instead of the vertices, we shall consider the midpoint of the rectangles. We shall have the first subinterval from -4 to -3, and then -3 to -2, from -2 to -1. In order to get the length of this rectangle, we shall evaluate the given function x squared plus 5x plus 8 using the midpoint of the subinterval. So from -4 to -3, the midpoint would be -3.5. So evaluating the given function at x equals -3.5, we shall have length equal to 2.75. Now for the second rectangle, we shall have it on the second subinterval, and the midpoint of the second subinterval is -2.5. Evaluating this given function, f of x equals x squared plus 5x plus 8 at x equals 2.5, we will have 1.75. So therefore, the length of this rectangle is 1.75. For the third rectangle, we shall have the third subinterval, and its midpoint is negative 1.5. So we evaluate now the function f of x equals x squared plus 5x plus 8 at x equals negative 1.5. Using our calculator, we will have 2.75. Now take note that the width of these rectangles are all equal to 1. Now to get the total area, we can have the shorter way, which is delta x times the sum of the lengths of the three rectangles. So delta x is 1, the length of the first rectangle is 2.75, the length of the second rectangle is 1.75, and the third is 2.75. Getting the sum, we will have 1 times 7.25, or simply 7.25. Now, as you can see, using the Riemann Sum Formula, in approximating the area of a region that has a regular shape is quite tedious. Is there any other way in finding the estimated area of an irregular shaped region? Yes, there is. That is by using the fundamental theorem of calculus, which states that if f of x is continuous on a closed interval from a to b and capital F of x is the antiderivative of f of x on the closed interval a from a to b, then we will have the definite integral of the function at the closed interval from a to b is equal to the antiderivative of the function evaluated at b minus the antiderivative of the given function evaluated at a. So with this, we would be able to approximate the area of the region. Now let's study first. Before we proceed, I would like you to take notes some integration rules for a definite integral. These are needed as we compute for the definite integral of a function. Now let's have the first example. We are asked to find the definite integral of negative x cubed plus 3x squared plus 1 at the closed interval from negative 1 up to 3. So applying the fundamental theorem of calculus, we would have we need to get the antiderivative of the given function first. So since we have negative x cubed, that would be getting the antiderivative of x cubed. We will have 3 plus 1 in the exponent, and then copy that expression in the denominator. Then we will have to do the same to the other terms. Now take note, 1 can be written as 1 times x raised to 0. So we shall have 0 plus 1. Okay. Evaluated from negative 1 up to 3. Now simplifying this, we shall have negative x raised to the 4th power over 4 plus 3x cubed over 3 plus x evaluated from negative 1 up to 3. Simplifying this further, we shall have negative x raised to the 4th power over 4 plus x cubed plus x evaluated from negative 1 up to 3. Now that we're done determining the antiderivative of the given function, we are ready to evaluate. First, we use the upper limits. We have negative 3, negative of 3 raised to 4 over 4 plus 3 raised to 3 plus 3. Now, we deduct this expression. Simplifying, we shall have 81 over 4 plus 27 plus 3. Then we have negative 1/4 minus 1 minus 1. We shall have 9 3/4 in the minuend. For the subtrahend, we shall have negative 2 and 1/4. Now simplifying further, we shall have 9 3/4 plus 2 and 1/4, and simplified will give us 12. So that's it. That's the definite integral of the given function at a closed interval from negative 1 up to 3. Let's have the second example. Now we are asked to get the definite integral of 4x raised to 1/3 at a closed interval from negative 1 to 3. We get first the antiderivative of the given function. So we will have first the antiderivative of the function. Then we simplify. Now to simplify the complex fraction, we need to change the operation to multiplication and then get the reciprocal of the denominator. And get the reciprocal of the denominator. Simplifying, we can cancel this 4. So we will have 3x raised to 4/3 evaluated from negative 1 up to 3. Now we replace x by the upper limit, and then here we have the lower limit. And then here we have the lower limit. Now we can expand 4/3, so that can be equal to 3 raised to 1, and here we have 1/3. Then the subtrahend will just be equal to 3. Simplifying, we will have 9 times the cube root of 3 minus 3, or this is approximately equal to 9.98. This time, let's have a trigonometric function. We shall apply the same strategy. We have to get the antiderivative of the given function. So first, we can rewrite to have a much clearer view of the given function. We can write 2 before the integral sign, so we can see that the function that we need to get the antiderivative is cosine x. We get the antiderivative of cosine x, so we will have sine x. Then we copy this, evaluate it at negative pi over 4 up to negative pi over 6. So we now replace x by the upper limit. Simplifying, we will have, we can use our scientific calculator in simplifying the given expression, but make sure that your calculator is in radian mode. Now simplifying this, we would be able to get 0.4214213562373, or approximately equal to 0.41. Okay, I hope you were able to get that. And finding the definite integral of a trigonometric function. As I have said a while ago, we can use the concept of definite integral in approximating the area bounded by the given functions y equals 1/2 x squared, x equals 1, x equals 2, and y equals 0. All we have to do is to determine the closed interval at which we are considering the said curve. So using this, we would be able to determine the closed interval from 1 to 2. And the function that we need to evaluate is 1/2 x squared. Now, simplifying this can be equal to 1/2 times the definite integral of x squared at the closed interval from 1 up to 2. Now we get the antiderivative of x squared, so this can be equal to 1/2 times x raised to 2 plus 1 over 2 plus 1, evaluated from 1 up to 2. So simplifying, we will have 1 over 2 times x cubed over 3, evaluated from 1 to 2. So we will have x cubed over 6, evaluated from 1 up to 2. Now evaluating the given function at x equals 2 and x equals 1, we will have 2 cubed over 6 minus 1 cubed over 6. So we will have 8 over 6 minus 1, 6. So that is 7 sixths, or 1 and 1 6. In decimal, we can approximate. In decimal, it is approximately equal to 1.17. Okay, which is closer to our midpoint Riemann, which is closer to the value that we got when we used the midpoint Riemann sum formula. Now let's have another example. Also apply the concept of the definite integral in approximating the area beneath the curve f of x equals x squared plus 5x plus 8 and above the x-axis from x equals negative 4 to x equals negative 1. So we write the expression in this way: definite integral of x squared plus 5x plus 8 at the closed interval from negative 4 to negative 1. And then we get the antiderivative of the function. So we will have x cubed over 3 plus 5x squared over 2 plus 8x, evaluated from negative 4 to negative 1. Now we simplify. So now we evaluate the antiderivative. Using the limits, so we will have negative 1 raised to the third power over 3 plus 5 times negative 1 squared over 2 plus 8 times negative 1. This will be our minuend. And then the subtrahend, we shall evaluate the antiderivative of the given function at x equals negative 4. So negative 4 raised to the third power over 3 plus 5 times negative 4 squared over 2 plus 8 times negative 4. Okay, so here we will have 1/3 plus 5, negative 1/3 plus 5 simplifying, we will have negative 1/3 plus 5 halves minus 8. For the subtrahend, we will have negative 64 over 3 plus 80 over 2 minus 32. And then we get the LCD. We will have 6. So we will have negative 2. Then we have 15. And then 48. Okay, then we just simplify this. 64 over 3 plus 40 minus 32. So we shall have 45 over 6. When simplified, this is equal to 7 and 3, 6. And then reduce further, we will have 7.5. So that is the approximated area beneath the curve f of x equals x squared plus 5x plus 8. Now let's try to use the concept of the definite integral in approximating the area bounded by the curves f of x equals x squared over 4 minus 1 and g of x equals negative x squared over 4 plus 1. Now, to have a visual grasp of the area, we need to graph the functions on the coordinate plane. Now, using GeoGebra, we will have this graph. So, in this case, we will look for the area on this portion. Now, first we have to determine the closed interval at which the curves are being considered. We replace the name of the given functions by the actual expression. So we will have negative x squared over 4 plus 1 minus x squared over 4 minus 1. And then we simplify. So we will have negative 2 to positive 2. That's the closed interval we are focusing on. Now simplifying, we will have negative 2x squared over 4 plus 2. We can cancel the greatest common factor, which is 2. So this would be negative 1, and then this is 2. So we will have negative 2, definite integral of negative x squared over 2 plus 2. Now remember that when the lower limits and the upper limits are additive inverses and the function is even, we can simply evaluate this using the rule. So instead of negative 2 in the lower limit, we will have 0 and the upper limit is 2, and we just multiply everything by 2. So we will have negative x squared over 2 plus 2. Now, getting the antiderivative of the function, we will have negative x cubed over 2 times 3 plus 2x evaluated from 0 to 2. Then we apply distributive property. So the first term will just be equal to negative x cubed over 3. The second term would be 4x evaluated from 0 to 2. And then we evaluate the function at x equals 2. Minus the function evaluated at 0. Now, since we have 0 divided by 3 and 4 times 0 is also 0, then the subtrahend will just be equal to 0. So we'll just focus on the minuend. We will have negative 8 over 3 plus 8. Now the LCD is 3, so we will have negative 8 plus 24 over 3, that would be 16 over 3, or 5 and 1/3. Hence, the area bounded by the curves f of x equals x squared over 4 minus 1 and g of x equals negative x squared over 4 plus 1 is approximately equal to 5 and 1/3 square units. I hope you were able to get that, because your knowledge for these concepts can be applied just like in the first sample problem that we have. As couturier, Jean designs clothes that would perfectly fit her customer's preference and making sure that her designs are authentically hers. So she planned to cut pieces of cloth in a shape that looks like the graph of the function defined by f of x equals x cubed minus x and y equals 0 at the closed interval -1, 1. About how big is the design if 1 unit is equivalent to 1 centimeter. Now, to have a more grasp of the given region, we graph using Desmos. We graph the function x cubed minus x. So we have this curve. Now, we also have the x-axis, having an equation y equals 0. And then we have to identify the interval from -1 to +1. So therefore, we only have to consider only this region. So with this, we would be able to imagine that if we draw rectangles on this particular region, we would be able to get the area of the said region. Now, using the midpoint Riemann sum, we will have these rectangles, and let's say we decided to have 5 of this, so we can have this approximation. So all we have to do is to get the sum of the area of these rectangles, then we would be able to get the approximated area of the region. Now, in order to save time, now using the definite integral, we will have closed interval negative from -1 to +1, and then the function x cubed minus x dx. Now, if you can still recall in the set of rules that I have presented a while ago, if the function is odd and the lower limit and the upper limits are additive inverses, then the definite integral is equal to 0. So let's see if this is really equal to 0. Now we get the antiderivative of x cubed minus x. That would be x raised to the 4th power over 4 minus x squared over 2, evaluated from -1 to +1. So we will have 1 raised to the 4th power over 4 minus 1 squared over 2 minus -1 raised to the 4th power over 4 minus -1 squared over 2. Now, as you can see, we will have 1/4 minus 1/2, the same as the subtrahend 1/4 minus 1/2. Simplifying this, all of this will be equal to 0. But the problem is, we cannot accept that the answer would be 0, since we can actually see a region. Therefore, its approximated area should be more than 0. So with this, we have to show that we will not be arriving at 0. As you can see, this portion of the graph will have an area that is equal to a negative number. Take note, when the region falls below the x-axis, the definite integral will have a negative sign. No exception. Which is, if this function is evaluated at this interval, we can subdivide the intervals in such a way that it is still continuous, or that there's no gap in between the intervals. So from the interval from -1 to 1 can be from -1 to 0, and then from 0 to 1. So this will be our lower limits, upper limit on the first addend, and that corresponds to this region, while the second addend corresponds to this. Now, since this region falls under the x-axis, the definite integral will have a negative sign. So that means that the negative sign tells us that the location of that region is below the x-axis. So since this will give us a negative value, we need to get the absolute value of this definite integral. Let's continue the solution. So getting the derivative of the given function, we will have x to the 4th power over 4 minus x squared over 2. Evaluated from -1 to 0, plus the absolute value of the antiderivative of the given function, evaluated from 0 to 1. Now, evaluating the function at x equals 0, we will have 0 over 4 minus 0 squared over 2 minus -1 raised to 4 over 4 minus -1 squared over 2. And then we have the absolute value of upper limit is +1 over 4 minus 1 squared over 2 minus 0 over 4 minus 0 squared over 2. Now, we simplify. This is equal to 0 minus 1/4 minus 1/2. And then we have the absolute value of 1/4 minus 1/2 minus 0. So we will have negative of -1/4 plus the absolute value of -1/4. Simplifying, we will have 1/4 plus 1/4 is equal to 1/2. Therefore, the area is approximately equal to 1/2 centimeter squared. Now let's work on sample problem number 2. A restaurant owner would like to create a partition between customers in compliance with the ITF requirements in accordance with the health protocol for COVID-19. He plans to use plexiglass and cut it in a shape formed by the functions defined by f of x equals x squared minus 2 and the x-axis at the closed interval from -1 to +1. About how many square meter is the partition if 1 unit is equivalent to 1 meter. Now we use the concept of definite integral in solving the given problem. Now we graph the functions given in the problem. So we have f of x equals x squared minus 2, the green color, and then we have x equals -1 and then x equals +1. Now we write the definite integral that will describe the situation. So the closed interval is from -1 to +1. And then the function is x squared minus 2. Now remember that whenever we have additive inverses on the upper limit and the lower limits, and we have an even function, we can just multiply by 2. So instead of having -1 in the lower limit, we will have 0, and then the upper limit is 1. Then we have the function x squared minus 2. So getting the antiderivative of the given function, we will have x cubed over 3 minus 2x, evaluated from 0 to 1. Now we will have 1 cubed over 3 minus 2 times 1 minus, we will have 0 cubed over 3 minus the quantity 0 cubed over 3 minus 2 times 0. So simplifying, we will have 2 times 1/3 minus 2, and then everything will be 0 here. So we will have 2 times 1/3 minus 2 is equal to 1 minus 6 all over 3. So we will have 2 times -5 over 3. Now simplifying, we will have -10 over 3 or -3 and 1/3. Now since the value that represents an area should not be equal to negative. Now since the value of an area, since the smallest value of an area is 0, it can never be equal to negative, then this contradicts the concept of an area. So we recall that the region that we are working on belongs to the region or falls below the x-axis. That is why it has a negative sign. So all we have to do is to get the absolute value of this number. Hence, we will have 3 and 1/3 square meters. Now let's have sample problem number 3. A geodetic engineer was tasked to determine how big is the land area of a lot in which the boundaries are determined by 3 roads. One of the roads can be modeled by the function f of x equals the square root of x, and the 2 roads are perpendicular with each other. About how many square meters is the land area of the lot if one of the perpendicular side of the lot is 20 meters? Now, to have a more vivid visualization, we graph the given functions. Graphing, this will be the lot being described in the problem. Then we have the interval from 0 to 20. So we will just consider the closed interval from 0 to 20. And then the function is the square root of x. Now, getting the antiderivative of the given function, we will have x raised to 1/2 plus 1 over 1/2 plus 1 evaluated from 0 to 20. Now, we will have x raised to 3/2 over 3/2 evaluated from 0 to 20. Simplifying further, we will have x raised to 3/2 times 2 over 3 evaluated from 0 to 20. So the function would be 2/3 x raised to 3/2. Now we evaluate the given function at x equals 20. So we will have 2/3 times 20 raised to 3/2 minus 2/3 times 0 raised to 3/2. Now the subtrahend will just be equal to 0, so we'll just focus on the minuend. So using our scientific calculator, we will have an area that is approximately equal to 59.63. Therefore, the lot is 59.63 square meters. I hope you were able to grasp our lesson for this day. Now let's check whether you were able to attain all the goals that we have set at the start. Can you now approximate the area of a region under a curve using the 3 types of Riemann sums? Can you define the definite integral as the limit of the Riemann sums and solve real-life problems involving areas of plane regions? Congratulations if you have answered all 3 yeses.